talk about the difference in a moment. So what I'm going to do is scenario number 1, box falling. It's the simplest case. So the first thing I'm going to do is I'm going to draw a picture of a box falling. Even though I'm ignoring air resistance, those are just to symbolize that there's some ripples in the air because it is falling, but it's magically not affected by the air at all. The hash marks indicate something that we are considering to be still. This is the ground, box falling. Any questions on what's happening here? We can do a visual demonstration if you want, if you need. All right. So when you're doing a force diagram, the first thing I recommend that you do is you draw the two objects. Now in this case, it looks very much similar to it, but you're drawing the two objects that you're going to put forces on. Make sure there's enough space in between them so that it's very clear what you're doing. And then we go to our checklist. Is there any tension in this problem? Is there any friction in this problem?
No.
Is there some mysterious force that I mentioned as part of the problem? Is there a normal force in this problem?
Not yet.
Is there a gravitational force in this problem?
Yes.
More specifically, weight. So, it acts, it's a pulling force, so the four arrows are pulling towards each other, or pointing towards each other. You're drawing the forces that are acting on that object. You're not drawing the forces on the source, but on the recipient. So weight is pulling down on this object, and I label it cleverly with a W, and they come in pairs, so there's a force acting up W. So I've got two masses, small one near a large, small one near a huge one. I assume that this distance, if it's to scale, not that far, size of a box, about 1.5 boxes away. Arrows pointing towards each other and is directed towards the center of mass of the other object. So, done. We are done with the first one. Some rookie mistakes. Go for a demon color. Some people like drawing the forces on the source instead of the recipient, so this is getting Mr. Yuck sticker right there. Don't do that. Another rookie mistake. I've seen this way too many times. I have no idea what the student is thinking in terms of which force is acting on which object. Again, Mr. Yuck sticker. And I guess the other one in that similar vein, not separating them. Am I trying to figure out which force is acting on which object? All right. Questions before I talk about what a free body diagram looks like? All right, so the free body diagram . Really? Looks a whole lot similar to it. It's other than a free body diagram, you basically, instead of drawing a box here, you draw a point. Box. Ground. The issue I have with it, and one of the reasons I don't do a free body diagram is, one, I don't feel like writing the words. It's easier to draw the picture than to write the word out. But the other one is that from my engineering training, especially civil engineering, where you're looking at, I've got a beam, and there's a mass distribution across the whole thing. How does the beam flex? Well, where the force is applied matters. At some point, we cannot assume that this is a point mass, that this does have depth to it. There is friction acting because of the surface, the average surface throughout the whole thing, and so forth. So from an engineering point of view, I feel like this is a better representation than that. However, physicists really like doing the dots. All right, questions before we do the next exciting installment. We're gonna do box on ground. All right, here we go, box on ground. So the first thing I do is I draw my picture and I have a box sitting on it. Let's label it for generations to come. Box on ground. So when doing the force diagram, the first thing I'm going to do is I'm going to draw a picture of the box. I'm going to draw the picture of a ground with enough space in between them so that I can draw my arrows without having to cram them.
But we're supposed to imagine the box is on the ground.
Yes, yeah, I've just drawn a box, I've drawn the ground. I try to draw them in the same orientation because for me it helps keep it clear, but this is what's actually happening. Box is sitting on the ground.
Exploded diagram.
Yeah. All right, we've got our checklist. Is there anything that we can eliminate?
Other. Tension. Friction because you didn't specify any desired motion.
Nor is there any implied. Now you might look at this and go, well, that's not exactly level. If it looks like I meant it to be level, then probably it's supposed to be. If in doubt, ask. But I don't play the game where it's at a 1 degree angle. Can't believe you missed that. So if it looks like it's supposed to be level, it is level. All right, so we have normal force, we have gravitational force. We have both of these here.
Yep.
All right, which way is the gravitational force? I think that's the simpler one. Which way is the gravitational force acting on the box?
Towards the ground.
Specifically towards the center of the planet. And they come in pairs. Where's the other one?
Toward the box.
Acting on
The ground.
now properly. This is just, in a sense, a crude sketch. This, in terms of the whole scheme of things, it is leading us towards getting the equations to be able to actually solve something. We're just not there yet. These arrows, if we were being really picky about it, would be the same length. All right, normal force done. What about gravitational force? Oh, sorry, that is gravitational force. What about normal force? Is there contact between two objects?
Yeah.
All right, so good chance there's a normal force there. Which way is the normal force acting on the box?
Upward.
It is. If suddenly there was a cave in here and we lost the ground, that box is going to fall. Therefore, the ground must be holding it up. So there's a normal force acting up, and they come in pairs.
On the ground, pointing down.
Absolutely. If we were doing a person standing on the ground, this right here is what's causing the footprints.
Is that why?
Thank you very much. That was not that one. That normal force right there is what's causing the footprints. All right. Questions here? Coach is about to do the next incredibly exciting installment, something that you'll be talking about for generations. Imagine your grandkids sitting around. Tell us a story about the force diagrams. Box on ground. and I'll label that box A and box B. All right, so I'm gonna draw my box A, draw my box B, draw my ground. You don't officially have to put them in the same orientation as they are there, but again, to me, it's very helpful to do that because especially when you're doing pairs, it's nice to know that, well, that one's gonna go up, the other one's gonna go down. It saves a little bit of time in mental processing. All right. What can we get rid of?
Friction.
Which one?
Friction. Tension. Other.
See how simple this is? Right there, we got rid of 60% of the problem. Gravitational force?
Yep.
Normal force?
Yep.
All right. You want to start with which one?
Gravitational,
Okay, which way is gravitational force acting on A?
pulling it towards the center of the earth.
Where's the other part of that pair?
The center,
The ground up towards A.
yeah. I was thinking how to word that right.
The most common mistake I see here is people putting weight, the other part of that force acting up on B. Weight does not require contact. Gravitational force does not require contact. All right. Anything else with gravitational force?
It's pulling B towards the center of the earth.
And,
B is pulling the center of the earth towards it.
all right. I've deliberately made a mistake here because I want to point out another rookie mistake. What is wrong with this diagram?
It doesn't tell you which force belongs to which when it comes to the gravitational force on the earth.
Why is that a problem?
You don't know which one's which.
And also, if this were true, if this actually were accurate, we are claiming that A and B weigh the same thing. And you probably should not assume that. So the subscript that you put down really is not particularly important as long as you get the pairs right. So if that's A, that's A, that's B, that's B. Some people, I like to do subscripts that have some meaning to the diagram itself. Other people, just the first pair, they'll put 1, then 2, then 3, and so forth. There's not anything inherently wrong, it just saves a little word brain processing time. All right, those are the weights. Normal force.
There's a normal force between A and B.
Okay, which way is it acting on A?
It's pushing up,
And B?
and it's pushing down on B.
All right, any others?
Normal force on B in the ground.
Okay, acting which way on B?
Up.
And the ground?
Down.
Now, just, you probably have noticed, generally when I do my subscripts and I do it based upon in the diagram, I usually start at the top and work my way down. I mean, equally, if I start at the bottom and work my way up, then I probably have a G here for ground and B here for B, but I tend to start top and go down. All right, so we've done the force diagram, absolutely beautiful thing. Let's actually apply this. There is an actual application to this. Oh, suppose box B is sitting on the ground, I take box A and I drop it and it smacks into box B. When it smacks into box B, what would be different about this force diagram? What would change if A is just made impact?
Would there be some sort of like inertial force or something with the mass?
Nope.
The normal force would be higher.
That's really, the size of the arrows is the only thing that would change, but in terms of actual arrows, that's it. It's the same. In terms of setting up for a problem, it would look identical. If the box is in equilibrium, those would be the same length. If it is just hit and it's starting to stop, this would be a larger error than that. All right, application. I got ground, I have a scale, analog scale, and I'm standing on the scale. Let's do the force diagram. I got a person, I got a scale, and I got the ground. What does the force diagram look like?
Basically exactly the same as that one, right?
I'm gonna change subscripts because that's just my thing. I got weight of person, weight of person, weight of scale, weight of scale, normal force on person, normal force person exerts on scale, and then normal force from scale, normal force back. All right, all I've done is change subscripts. Patrick, you had a question?
No, I was just trying to visualize.
Okay. Did you visualize?
Yeah.
Okay. So, what does the scale read? I stand on the scale, what is it reading?
220 pounds.
Not necessarily.
Because it depends on what planet he's on.
Let's assume Earth.
Are you looking for one of our arrows?
That probably. I mean, you could,
It would be the normal force between you and the scale.
yes. It is not measuring my weight because my weight is between me and the ground. I am not exerting my weight on the scale. I'm exerting this normal force. The scale is measuring the normal force I exert on it. If I start bouncing on it, I don't know what point, if all of you bounce on an analog scale at some point,
Yeah, more or less.
yeah, you notice the needle goes, or the dial underneath the needle goes shooting back and forth. It does not mean your weight is changing. What's changing is the normal force. So if I bounce up, so I'm pushing down on the scale in order to accelerate myself upwards. If I'm accelerating upwards, normal force is bigger than my weight. As I land, so if I jumped up off the scale and as I land, I'm coming like this, I'm moving in that direction and slowing down. Therefore, my acceleration is that way, opposite of velocity. And if my acceleration is that way, this has to be bigger than that. When I'm at the peak, so I bounce on the scale, I don't actually come off the scale, but I'm bouncing on the scale, I reach sort of a peak moment right there. So my velocity is this way, I'm slowing down, so acceleration is down. I reach the peak, then I start speeding up in that direction. Well, my acceleration is downwards, my weight is bigger than the normal force, so the scale will read less than my actual weight. It only is going to measure my weight if I'm in equilibrium. If the total acceleration is 0, then those have to add up to 0. So those will, and that's why we generally say it measures your weight, but in reality, it doesn't. If it actually did measure weight, then you could insert weight loss and weight gain. Just bounce a little bit. Hey, I weigh 50 pounds. Hey, I weigh 300 pounds. We got time for one more. Questions before we do the one more? That's supposed to be touching. and the famous pulling box with rope. Couple things to note here. This is an ideal rope. The Sassen refers to it as a magic rope. Ideal rope, or string, or whatever it is. Ideal, it is massless, which means I don't have to worry about its weight. It is frictionless, so I'm not worrying about its turning the pulley. And it is stretchless. Which means that I'm not gonna have B bungee jumping down while A is just sitting right there. So if B moves a meter, A moves a meter. At some point, we will definitely do away with the frictionless. If I'm in the mood, I'll throw away the massless, but we start out with the simple case, and then over time, we can start removing some of the restrictions. This pulley, even though the rope is frictionless, it really doesn't, the pulley's not going to move, but we will just throw in, it is massless, it's an ideal pulley, massless, and frictionless. Now, when you are doing a problem like this, part of the question the students sometimes deal with is, what are we doing forces on? I mean, am I doing the right relationship between the pulley and the ground? So, on a problem like this, generally you break it into, I know we're dealing with A and B, the pulley really is inconsequential it's part of the ground, or I would give it to you and break it up for you, just so you know what I'm including, but right now this is saying that the pulley is part of the ground. Do not do the forces in between them. If you do, I probably would circle it and just write something like that, which is short for ignore. It's IGN. All right. F-dom. Can we get rid of anything?
Oh.
That's pretty much it. Okay, we're gonna start with weight.